It's interesting how often we allow very unusual things to become commonplace. That often leads us to think we understand them when we really don't. That's the case with almost everything that has to do with space flight, from how rockets work to how the toilet on the International Space Station flushes, something we've all wondered about, kept us awake at night. In Project 8, Get Comfortable with Visual Aids from the Competent Communication Manual, Lloyd Smith will discuss a very simple and very complex aspect of spaceflight that we've all seen on TV so many times that it's becoming commonplace. Help me welcome Lloyd Smith with Weightless.
It's true, the space age is about 50 years old, and roughly 1,000 people have flown in space. Even if you don't care about the space race, though, everybody in this room has seen the astronauts floating around on the International Space Station, often with things like pens and clipboards and whatnot floating with them, even blobs of water occasionally. It really looks kind of interesting, and we all think, well, they're weightless. Well, they're not. If you think about it for a moment, they can be. Suppose you have a 180-pound astronaut who gets launched into outer space. He floats around on the International Space Station, apparently weightless. Then he comes back down to Earth. Does he weigh nothing, or does he weigh 180 pounds? He weighs 180 pounds. His weight couldn't possibly have just gone away and then come back somehow. He couldn't have been weightless. And that's because he was not. The simple fact is that what we call weight is not something that's in all of us. It's actually a measurement of how hard gravity is pulling on us and trying to pull us into the Earth. There's a bunch of complicated math and physics theory behind this, but it's totally irrelevant, so I won't talk about it. But what it amounts to is that everything in the universe is attracted to every other thing in the universe. And the bigger the things are, and the closer together they are, the more they're attracted. So what that means is that the Earth below us is really big compared to each one of us, and it tries to pull us down. And the force with which it pulls us down is called weight. People who are, say, 180 pounds are pulled down harder than people who are 150 pounds because they have more atoms inside of them. And that's what it amounts to. But nonetheless, we've all seen these people floating around on the space station. So how do they do it? We need to think about a simple thought experiment. Once you see this experiment, you'll understand how it works, and you'll be able to impress all of your friends with your understanding of orbital mechanics, which comes up frequently. Suppose that Eric and I are on a baseball diamond. He's standing at second base, I'm at home plate, he's struggling to throw me the ball. If you think about that for a moment, this is Eric. You can see the resemblance. And here's me, okay? I'm at home plate. What Eric has to do when he throws that ball is to give it some force. Now, how much force depends on how far away he is from me. But at the same time he's throwing me the ball, gravity is trying to pull the ball down toward the Earth, right? Now, we all learned as little kids how hard we have to throw the ball, and depending on the distance between us. And so, if he's at second base and I'm at home plate, if we look at it from the side, it'll be pretty much a straight throw because Eric can give that baseball enough momentum to get it to me despite gravity trying to pull it to the ground, right? Makes sense. Now, suppose we do the same experiment with a slightly different set of rules. I'm at home plate, but Eric is out in deep center field. Okay? So he now has to throw the ball to me with a lot more force, right? And the reason is gravity is still trying to pull the ball down. Oops. So what Eric will probably do is throw the ball in an arc toward me, right? And that's what we all do in the real world when we're trying to throw something from a longer distance. Now, so what it amounts to is that every operation like this functions just this way. You have to put force on it to get it to where it's going to go, and the force has to be enough to counteract the gravity trying to pull it down to the ground. Now, if I were out here and Eric threw the ball the same way he threw it here, it wouldn't get to me. It would probably go like this, and get the ground somewhere in between.
That's true, Eric.
Right? In fact, we see this happen a lot when people are trying to throw out first pitches at baseball games. They're typically not very good, they don't throw it hard enough, and it hits the ground sometime before home plate. Now, let's extend our experiment a little bit. Suppose that Eric is still, or that I'm still at home plate, right here. But Eric is in Spokane. Now, what does he have to do to get the ball to me? He has to throw it a lot harder than he threw it in the baseball stadium, right? In fact, it'll probably go way up in the air. It has to get to me in Spokane. And that's the force he's going to put on it because gravity is still trying to pull it down to the ground, okay? Now, there's an interesting thing about this. Energy is conserved. It can't be created or destroyed. And so when the ball comes down to me in Spokane, it will come down with the same amount of force Eric had to give it to get it up in the air. That is not a ball I'm going to want to be standing there with a baseball mitt getting ready to catch because it might come out of the sky with enough force to kill me. Now, this is actually how nuclear weapons are delivered, by the way. It's called fractional orbital delivery system, FODS. They shoot them up in the air, way up in the air. They take a partial orbit around Earth and then come down on some folks whose day is going to be really bad after that point. Now let's think about satellites in view of this. We have the Earth. That's a sad looking Earth. We launch a satellite. Now suppose let's say Eric decides he needs to throw that ball to New York City. He needs to give it a lot more force to get it to me in New York City, right? Suppose he decides to get it to me in Paris. He has to give it a lot more force to get it to Paris, right? Now suppose he throws it so hard that it starts going around, but it misses the ground. It'll go into orbit, right? And that's how things get into orbit. It turns out there's a way to calculate how much force that is. You have to accelerate the object to 17,480 miles an hour. Anything at all, a golf ball, the Empire State Building, whatever you want to put into orbit, if you can get it moving along at 17,480 miles an hour, it will miss the Earth. And the fact that it misses the Earth, think about that for a moment. Have you ever been on a roller coaster that went over the top and you float in the seat for a moment or two? That's what the astronauts are doing. That's why they're floating around. They are falling around the Earth over and over and over. And because that action is taking place in what's called a relativistic space, everything is falling with them. The space station, their clipboards, their ballpoint pens, whatever. So it all appears to float. Right? They're not weightless at all. They're simply falling at 17,480 miles an hour. And now you understand weightlessness.
Oh, yeah.